Thank you. Okay, so then, oh, now we got to go through that again. Okay, so let's, okay, so this is what we did. And then since test 2, right, we're trying to see how to reverse the order. So given an exact accumulation function, let's go ahead and build an approximate accumulation function to then determine an approximate rate of change function, which will result in, again, this action of letting delta x get teeny tiny so that we have an exact rate of change function. Okay, so now we're addressing this other question in calculus. Given that you know how much of something you have, how fast is it changing? That's what we're on now. Okay. And so we're going to streamline this process, and it's going to go a heck of a lot faster than it did you know, in the reverse order, because we've already got these tools and we already understand what these pieces mean. Okay, so you had a homework problem that challenged you to do this process. Okay, so what did we have? We had a graph a of x that showed the area of a square as a function of the side length of the square, and in the picture already is a piecewise linear graph that's associated to a of x. Okay, so is the function a of x a rate of change function or an accumulation function? A of x. So what does a of x represent again? The area of a square as a function of the side length. Is that talking about how fast something is changing or how much of it you have? How much of it you have. So it's an accumulation function. Okay. Now, okay. So then when we have this L of x function, this piecewise linear function, okay, that is our approximate accumulation function. Okay. And in this picture, it seems like it's doing a pretty good job, right? You can barely see the distinction between the black graph and the red graph, right? So we've already done a pretty decent job of approximating our accumulation function, okay? So let's really dig into it, okay? So you had a couple of questions to answer in your homework. Let's talk about them. Now, you can take notes, but ultimately what's going to end up happening is you'll turn in this draft, but then you'll do it again, okay? So don't, like, ignore me and rush to try to fix your homework. Just take notes as you will, but, you know, don't freak out, okay? So, all right, so when we look at this, so right now, notice I've only got the red curve on here, okay? So this is so the red graph is my graph of a of x, okay? So this is the exact accumulation function, okay? And then what we can do is approximate it with the black graph, okay, which is my L of x. So the black is L of x, okay? YL, linear, okay, not too far of a stretch. Okay, so but what did I do exactly? So for L of x, were you able to see the pieces? Where did the pieces fall? So from 0 to 0.2 was one interval, and then from 0.2 to 0.4 was another, from 0.4 to 0.6, 0.6 to 0.8, and then 0.8 to 0.1. So delta x for each of these is 0.2, right? Okay. Now, in order to actually answer some of these questions, though, I wanted you guys to find the average rates of change of a of x associated to each of these intervals. Okay. So what we've done is we've split up our function into chunks, right? So I've got this chunk here and then this chunk here. So how did you do it? Were you able to find these average rates of change? Who wants to talk me through it? So okay, better yet, what did you get for the first interval? What was the average rate of change that you computed? Point what? 2.5? Okay, and for the second interval? What did you get? 0.75? Is that what everybody got? 0.8. Oh, so we should maybe talk about how we do this. Okay, so if I wanted to compute the average rate of change over this second interval, what would I need? How do you get an average rate of change? Okay, so we're looking at changes in y over changes in x, right? Okay. So for this particular interval, what are my x and y values? At this point, what is the ordered pair associated to that point? 0.2 and 0.04. Okay? And then for this point, how did you get that, by the way? Did you have to guess? Right. So remember, a of x is the area of a square with x as the side length. So if your side length is 0.2, then your area is going to be 0.04, right? So we could use, like, we actually know what a of x is as a function. We have the entire function definition, if you will, okay? So we don't have to guess. We can actually come up with the exact values. So then at 0.4, what is the corresponding area? 0.16, right? So then if I wanted to compute the average rate of change for this second interval, okay, so we'll call this the average rate of change over interval 2, okay? Then I could say that would be, so what is the change in x? Or, sorry, the change in y? Yeah, right? It's literally the change. So we talked about how differences allow us to compute changes relative to a change in x. So 0.4 minus 0.2, right? And that gives me what? Am I doing this right? What is that value? Hmm? 0.6? Okay. So now we've got a rate of change value for this interval. So I could write that, as 0.6 here. Okay. Now, when I write this number, right, next to this line segment, what am I talking about? Am I talking about the line segment? Is the line segment 0.6? Does that make any sense to say a line segment is 0.6? What am I talking about? What is this number relative to that line segment? It's the slope, right? So we're talking about the rate of change here. So we're talking about the slope of this line segment, okay? And then we could keep on going, okay? And we could do this calculation for each of these intervals. How are we feeling about that? So far, so good? Okay. So then, once again, though, so let's actually concentrate on the meaning. So I think this one, you end up getting 1 for the third interval. Okay. So once again, so we've talked about what this number represents graphically, right? It's the slope of the line segment in that interval. But what is the meaning? What would you say if you were to interpret that value in terms of a of x and x? What are we talking about? So maybe take a minute, talk to your neighbor, figure out how you would describe the meaning of this value. right, let's see, Philip? Okay, so the average rate of change of the area function over the interval from 0.4 to 0.6. What is average? So that phrase, average rate of change, is a loaded phrase. What does that mean, Erin? Okay. Okay, so you had a lot in there. That was good. So the meaning of this value 1, it is the constant rate of change for the L of x function in the third interval. Okay, and it yields the same change in area with as the A of x function does over this third interval. Okay. It takes a minute to explain what this means, right? If you ever interpret the meaning of average rate of change and you give like a 2-word answer, you're not there, right? It's a complex idea. There's a lot of layers to it, okay? So, all right. Okay. But we've done it, right? So we've computed average rates of change over consecutive intervals of our accumulation function, right? So where would we go next with this? So I've got a couple of values. I don't remember what they are. Does anybody want to tell me what the next interval? 1.4, 1.8, and 2.2. Okay, you probably had to estimate that one because it didn't quite, like, it got cut off, right? Okay, so once again, if I was looking at representations, right, I've got changes in x and corresponding changes in y. Okay, changes, the same change in x, and now this is a different change in y over this interval, right? So if I were to compare changes in y, are they staying the same? They're changing? What's happening? They're changing, right? And so the fact that we're keeping delta x the same, but delta y is changing, that means that the constant rates over these intervals are different, right? And we see that in these numbers. And so if I wanted to talk about the behavior over the interval like 0 to 1 point, or to 0 to 1, right, then would I be talking about a constant rate of change for the entire interval? So from 0 to 1 over this entire interval, am I looking at a constant rate of change for that entire interval? No. This is a changing rate of change, right? Because we split it up into 5 smaller pieces. And within each piece, there is a constant rate of change, and that's what you computed, right? Okay. But it is a changing rate of change. Okay. So what can we do from here, right? So remember, our big picture goal is to end up with an exact rate of change function, right? Because I started with an exact accumulation function. So my goal now is an exact rate of change function. So let's explore what we can do. Oh, I went too far, too fast. Okay, wait, let's go back here. So when we were looking at those computations that you guys gave me, say from here to here, or let me actually make this more general. So let's make this totally general. Okay. I don't want you to have values down here anymore. Okay. And instead I want you to just think about, and this is no longer like a of x in particular. This is now just going to be some function f of x. Okay. And I want to repeat this process. So we're generalizing now. Okay. So let's say I've got some interval from here to here, and I've got a current x value right here. Okay? So if I wanted to find the average rate of change over this interval, what would I do? That is the question. What do I need to know and what would I do? Take a second. Think about it. Or if you already have an answer, see if it's the same as what your neighbor thinks. Okay? So what things do you need to know in order to be able to do this? How do we find an average rate of change? Change in y over change in x, right? So if I want to compute an average rate of change, I need x values and I need y values, right? That was important. Okay? I said that quickly, but that was important, okay? So how could we talk about the x values that I've drawn in this image? Yeah? All right, so this, yeah, that was perfect. Okay, so this x value right here, this is left of x, right? We spent a lot of time building up this function. We better use it, okay? So if this is left of x, and then this interval is some length, we'll just call it delta x, okay? So then this will be left of x plus delta x, right? So then, all right, so now I have x values, but I need the corresponding y values, right? So how would I get the corresponding y values? You said a of left of x? Somebody? I heard it. Okay, yeah, but let's remember we're going to use a general function. So instead of a, we'll call it f. Okay. Do I have enough? There we go. Okay, and then over here, we've got the same thing, right? Left of x plus delta x, and then the corresponding y value is going to be f of all of that, right? Okay, so then if I want to compute the average rate of change over this interval, then what is it going to be? Erin? Okay, I'm going to keep writing it the long way, but yes, this is rate of x. Okay, right, so left of x plus delta x minus left of x, that's just the width of the interval. Okay, which is why I chose not to use right of x, right, so that we could actually see that. Okay, now, so this expression is the average rate of change over this entire interval, right? So then if I wanted to know the rate of change at my current x value, okay, then I would actually assign that value to my current x, okay? So now we've defined a rate of change function given a general accumulation function, okay? So this function, again, it inputs current x, right? And it outputs the average rate of change over the interval containing that x value where we've already made a choice for what delta x should be. Okay? How is that? Okay? Okay. So let's see what this all looks like in graphing calculator. Okay? So well, let's go back to our specific function. F of x is x squared. Okay, so we're talking about, again, the area of a square given the side length x. So f is what? I just said it, right? What type of function is it? It's an accumulation function. So in particular, f gives the accumulation of area of a square, right? As what happens? As the side length increases from what? From 0 to okay, so you're thinking of a very specific value, but this function, right? So the function inputs x, which is the current side length of my square. So the output is the area that has accumulated as the length increases from 0 to x, that current value. Okay? So over here on the right side, I've got a graph of that accumulation function. Okay? And then what we just did was say, all right, well, if I want the rate of change function, so r is what? I've got r of x defined just as we did on the slide. So it's f of left of x plus delta x minus f of left of x, all divided by delta x. What is that showing us? What is it representing? So r gives the constant, or we've been using average rate of change, right? For what? If I just stop there, I'm not being specific enough. For the current x relative to so what are we talking about? We're computing a rate of change, the current value of x. What piece haven't I talked about yet? The interval, right? Relative to the, so how about this? Relative to the delta x interval containing the current value of x. Okay? So that's what we've managed to define. Okay? So riddle me this. I've got an equation down here that's going to graph r of x in this left space. Okay? What is it going to look like? Cool. You want to go for it? Should we go there? What's it going to look like? Piecewise linear? Okay. Talk about it. Think about what is it going to look like. So I'm going to graph y equals r of x in the left window. What is that going to look like? Questions you can ask yourself to help. What is the input and what is the output of the r of x function? All right, what you think? Moises? Okay, that's all right. Anthony, are you here? Anthony? What you think? One constant value? So the whole way across this picture is just going to be one constant value? Oh, so what would be important to think about? Delta x. So in this case, delta x is 1. And this axis goes from 0 to 4. So my intervals are length 1. So you've got a constant, there's something about a constant value. Okay. Do you still think it's going to be just one piece? Not sure? Going to be 4 pieces? What do you think? Okay, so predicting a step function. And some other things are important, right? So I highlighted the delta x, but we've also got an a, right? Remember that we have to talk about where it starts too, okay? So let's go ahead and graph this bad boy and see what we get. Ha, ha, ha. Okay, so step function, right? Piecewise constant function. And again, that's because we're inputting current x values and outputting the average rate of change, which is a value, right? One numerical value over a given interval, okay? A given delta x interval, okay? So then what are some things that we could do? Is this a very good approximate rate of change function? How would we make it better? Make delta x smaller. Making it smaller. Okay, so I can do that, right? And now we're starting to look really, really good. Like really, really good, right? Okay, so what else do I have control over? The starting place, right? Where do I start paying attention to my accumulation for my square, right? So I can change A. Now I want you to pay attention to what happens to this graph while I change A. Is anything super crazy happening? When delta x is really small, that starting value doesn't make a whole big difference. Okay, so I'm gonna momentarily switch gears, and I'm gonna show you another image so that you can see that. Okay, so here again, so now I've got x squared graphed, but without any domain restriction. I'm not gonna think about the physical area of a square context. I'm just gonna look at the function. Okay, and so right now I've got delta x at 2. And I can control, so down here I'm controlling the value of A, okay? And when I let A change, you see, like you can see some differences. But structurally, the approximate, so here, this dark blue right here, here's A, right? I finally got it to a level where you can see it in the image. So yes, some things are shifting. But overall, the structure of my approximate accumulation function, this piecewise linear function, it stays piecewise linear, right? No matter where I put A, okay? And then what we can do is we can make delta x smaller, and we can still look at that process happening, okay? But notice that those pieces, those linear pieces, they're still looking linear, and they're getting closer and closer to the graph, right? And so then when I let delta x be really small, you can't even see the pieces anymore, right? To make a judgment call about the influence of A. Okay, so A doesn't matter once we're at this level. Okay, it's still there in the background, but its influence on the big picture is minimal. Okay, so in fact, what are we doing? So A, sort of irrelevant at this point. Making delta x really, really tiny gives us a fantastic approximation. So what haven't I actually done? So So you guys are currently trusting me that, right, or you shouldn't actually be trusting me all that much. We've built it together that this, this expression gives you the average rate of change over delta x intervals. When you let delta x get really, really small, this r of x starts looking like a really nice function, okay? And so what I can do, in fact, is say that when delta x gets so small, it's as if I'm looking at an exact rate of change function, okay? So just like we did before, we take our approximate rate of change function, and as delta x gets super, super tiny, it's as good as if it were the exact rate of change, okay? How are we feeling about this? Now, something that I haven't done during this discussion is keep track of the piecewise linear approximation accumulation function, right? So just to make sure that we remember, because we don't want to forget everything that we've learned, everything in this class is connected, how would I write an equation to produce the piecewise linear approximation accumulation function? Whew, big mouthful. But I want you guys to tell me, how do I write the the approximate accumulation function to be able to graph it next to here and see that we're getting really good approximations when we let delta x get small? Is what I want clear? Piecewise, I want the L of x function. Okay, I want to know how you write the equation for L of x. Here's your hint. Linear function, okay? So think about it, talk with your neighbor, come up with an equation. seeing some people still trying to use sigma notation, summation notation. So remember, our goal right now is to produce a piecewise linear function. When you're trying to write a linear function, what are the components that you need? You need a constant rate of change. And what else? A point. Resume your conversation. Okay.
So, sigma notation piecewise linear are exclusive, right? So, you want them to do it line by line.
You've got R because that will produce your piecewise.
Sure.
I'm hearing some good conversations. Let's go ahead and bring it together so that we can make sure we get through it before the end of class. So, what's the general structure for a linear equation that we've talked about, that we've built up in this class from way early on? Do you guys remember? Yeah? Whoop, hold on. Okay, so you said y equals k times what? X minus a plus b. Okay, so and a really productive way of thinking about this is that your new y value, or your current y value, is your constant rate of change times your change in x, right, added to your initial y. Okay, so if we were to zoom in on some, some interval, some delta x interval, and we've got a current value of x that I care about. So I'm inputting this current value of x into my L of x function. Okay, my L of x function is supposed to be a piecewise linear function that's going to approximate this accumulation function. So visually, it's going to look like a straight line from there to there, right? Imagine that actually connected to the curve, okay? So over this interval, what is the rate of change? The constant rate of change. We just developed it, right? That was R of x, okay? So my constant rate of change is R of x at that current x value. How would I represent the change in x? So does this current x value contain the entire delta x interval? No, right? So this current value of x, when I think about the change in x, I'm really thinking about from this current value from the starting of that interval. Okay? So this linear piece, you could think of its starting piece as being this, or its starting point being this point. And we've already talked about how you represent that point, right? What's the x coordinate of this point? Left of x, okay? So this is left of x, comma, f of left of x, right? So here's my starting x value, if you will, and then here's my current x value. So when I talk about the change in x, I'm going to do x minus left of x, okay? And then I have to add to that my starting value of y, which was f of left of x. Question?
When we were doing accumulation, we took our left of x and we applied that rate over the entire interval. We are not doing that in the reverse order.
So we are finding the average rate of change by using the endpoints of a given interval, and that average rate of change does apply to the entire interval when we're approximating the accumulation, and then from there building the corresponding rate of change function. So let me erase what I've just written and show you. So here it is, right? Here is my rate of change times change in x added to the starting value within each interval. Okay, so I can delta x is really small right now. So over here, right, so you can see that, so this red graph, right, on the right-hand picture is my piecewise linear function, right? And because of the way we defined it using general terms, r and left of x, that's all we have to write. It automatically creates the pieces, okay? And then as we change delta x, that gets better and better. And so now you can see as I'm changing delta x to be smaller, the red piecewise linear function on the right side gets closer and closer to the actual exact accumulation function, okay? And so what we're doing is we're taking the slopes of these pieces and we're recording them on the left graph, right? Each of these pieces, those constant rates of change, those are those steps. And so I let delta x get really small, I get more and more steps, right? Because I've got more and more delta x intervals. And as they get so small, this becomes a really good approximation over here, right? My approximate accumulation function is now fantastic, okay? And so I can trust that the corresponding approximate rate of change function is actually getting pretty darn close to the exact rate of change function, Okay? And in fact, that's where we're going to have to go on Wednesday. Okay? So go ahead and turn in your homework assignment. What you're going to do is you're going to end up polishing it again for Wednesday, and I'll put something else on Blackboard for you as well. Okay? There is recitation today. You will take a quiz based off of what we've started since Friday.
Will it be possible to go over the test?
Yes.
I have recitation at noon.
Okay.
I think we'll have time.